And now, can we please welcome from Etron, and we have 3 people from Etron here. Who's actually going to be doing the main speaking? Richard Crisp.
Well, thanks for having me over today. So I'm going to tell you a little bit about some of the imaging products that Etron's sister company, Eyes 3D's developed. And then I was asked to please not give a marketing presentation, so asked to make it technical. So I'm going to get a little bit into electro-optical issues relating to imaging. So hopefully it'll be interesting. Eyes 3D is the company now that Etron's imaging products are made by and sold under that name, and so it was spun out of the company last year. And they're headquartered in Taipei, Taiwan. They have 49 employees. And mostly what they've been doing is developing ICs that are used for making 3D depth map cameras using stereoscopic techniques. And then alternatively, we've used some of those ICs to make 360-degree cameras as well. And so I'll show you a little bit on each of those. The offerings primarily today are ICs and then also camera modules. And mostly what we're finding most people are interested in today are the camera modules, because they want to go do something with them and they don't really want to make their own cameras. But some companies actually do want to make their own cameras, so we sell them the ICs as well. But we're actually primarily a semiconductor company. This is a list of the various modules that we have for sale today, and I think most of these things are available from stock, maybe not all of them are. One of our FAEs, Tyler Wynn, is with us tonight, and he's got a lot of details on these specific camera modules. But they basically, some of them have rolling shutters and some of them have global shutters. And some of them have higher resolution than other ones, and some of them have variations in the. We support various different baselines for the stereoscopic imaging, so that it gives slightly different sweet spots for the depth maps, and then some of them also incorporate a near IR pattern type illuminator, so that when you have a textureless surface or whatever, you can go ahead and get a stereo depth map from it. And then, of course, it also augments the low light operation as well. Additionally, we make a couple of different 360 cams. And I think these things are going to start getting some traction in the AR world. It's sort of a inside looking out kind of arrangement. I could well imagine somebody might want to throw one of these things on the top of a robot just for fun. So they can see around on all 3 sides, or all sides of it. But we have one that's 1920 by 1080 kind of resolution, and another one that's a little higher resolution, 2560 by 1440. And I know the first one's available through Amazon. I'm not sure about the second one, but any questions on availability on any of these things, we could ask either Tyler or Chung. I think Chung Lam's here as well. So the next thing I want to do is I want to talk generically about depth camera technology. There's some different ways in which people create depth maps. There's sort of 3 basic technologies that are out there. One is stereoscopic, and that's how we work, right? We've got 2 eyes. And that's how we acquire depth is that way. So that's probably the simplest method that's in use today that everybody would be familiar with. There's another one called TOF, or time of flight. And essentially what they do is they send a pulse of light out, and then they measure the amount of time it takes for it to return. And so you can extract depth information that way. There's another method that's called structured light, where there's sort of a pattern that gets projected out. It's a predetermined pattern, and then there's an image taken of the scene, and then the way that the pattern gets distorted is encoding information regarding the depth structure of the device. So you can extract depth information that way. And each of them, from what I've seen over the years, has their own set of areas where they work really well and other areas where they don't. And if you look at something like a self-driving car or whatever, you're probably going to see a merger of a whole bunch of different technologies to solve all of the problems. But I think in the robotics area, there's a fair amount of interest in getting a somewhat wide field of view, and to do so in all kinds of lighting conditions, particularly if you want to work outdoors. So those can be some issues with that, and I'll get a little bit more into that in a minute. But these are the basic trade-offs as I see them. On the horizontal direction, I show 3 different technologies. I show TOF, structured light, and stereoscopic, and then vertically I have these various things that are care about. So like, for example, on the left-hand side, outdoor operation, and then the next one is a featureless target. Another one is a wide FOV, another was depth accuracy, another one's high resolution, and then another's color camera. A lot of times people want a depth map, but then they also want a color image as well that a human's going to look at. So depending on which of these technologies you're using, some of these are easy to do and some of them aren't so easy to do. For example, outdoors, the TOF and structured light technologies oftentimes have difficulties working at range and giving acceptable low noise depth maps. And the reason is that you've got bright sunlight out there, and then you've got a near IR illuminator, and it's got to somehow or another be able to take an image of the near IR with a whole lot of near IR in the background from the sun. So that can be kind of a problem. On the other hand, they do really well with featureless targets because they're supplying an illumination source, and they can very easily measure, say, a white sheet of paper at an angle. On the other hand, a stereoscopic camera, if you take an image, stereo image of a big piece of white paper tilted at an angle, it may have difficulty getting a depth map from that, unless you happen to be projecting a pattern. So in this case, I've shown on this, I guess I don't have a pointer, maybe I do, yeah. I show that you can either have acceptable or poor, or excellent or poor results, depending on whether or not you're using an illuminator with the stereoscopic camera. Wide fields of view are pretty tough to do with the TOF and the structured light, and depth accuracy is pretty good on all of them. You can engineer them to work very, very well for whatever it is that you're wanting to do from a depth point of view. The TOF, because it uses a different type of a sensor that's actually designed for TOF applications, can have difficulty scaling up the resolution. And there's also some optical power issues associated with the illuminator. That also can kind of get in the way of increasing the field of view of a structured light sensor as well, and I'll say a little bit more about that. And then of course the TOF and structured light, those are primarily depth map technologies, and so they're not really color imaging technologies. When you use the stereoscopic method, you start with 2 color images, and then you can extract from that a depth map. So inherently you have the color image associated with the stereoscopic approach. So what I've done is I've taken that same chart and I've added some things to this. So when you look at the TOF and the structured light from an outdoor point of view, again, you're in bright sunlight. There's a lot of near IR in the bright sunlight. And so you either have to limit your range, or you got to boost up the power, or you got to narrow the field of view, or do all of those things in order to get an acceptable result. And there's limits as to how much you can boost the power. You've got thermal issues with usually they use a VCSEL type laser, vertical cavity side emitting laser as the light source. And that's a monochromatic wavelength, so you've got some eye safety issues there as well. So there's limits as to how much power you can pump through these things. They also get warm, and so you've got to worry about thermal issues. And then, you know, if you're going to run this thing from batteries, you don't want to run your batteries down too fast as well. And so those are issues both for TOF and also for structured light. When you look at wide fields of view, there's a couple of issues there. If you've got a really wide field of view with a TOF, then suddenly I've got to bathe a much wider area with the light. So again, I'm kind of power limited. There's only so much optical flux that I can put out without causing eye safety issues and having to have an enormously powerful lamp, if you will, for illumination. So ultimately, those are going to limit your field of view that you get for those technologies like TOF and the structured light. Likewise, in the high resolution, one of the interesting advantages of the stereoscopic approach that we're using at Etron or ICE 3D, is the fact that we just use ordinary image sensors that are built in high volume for the cell phone market, notebook computer, and so on. So those come in very high resolution. You know, you can easily get 20 megapixel sensors these days, and so on. So if you want to get a wide field of view, then you know you can pick an appropriate optics and pick an appropriate sensor size, and there's many you can choose from, and you can build that pretty readily with a stereoscopic camera. With a TOF sensor, because the sensors themselves are designed for TOF type measurements, they have oftentimes a split pixel that's used for integrating to measure the time delays. Those have to be actually engineered for the field of view involved, and so they also tend to use fairly large pixels for reasons I really don't want to get into right now. And so when you combine the idea of large pixels with a lot of them, then you get really large pieces of silicon that form the sensor, and those start getting very expensive, both for the silicon as well as the optics that you would have to put in front of it as well. And I'll touch on that a bit in a moment. Okay, so now what I want to do is I want to shift into talk some about the physics of imaging. And I have no idea about everybody's background in here, so this may be embarrassingly simple for some people, and it may be too advanced for some people, so I don't know. I'm just kind of, hopefully it'll work out. The first thing is, let's talk about how do we actually capture an image. So, you know, we have a solid state image sensor. Generally, they're reverse biased junctions, and in the potential well, we can collect photoelectrons that come in from light coming into using the photoelectric effect, which Mr. Einstein got a Nobel Prize for. The photons interact with the silicon, they create whole electron pairs. Those are charged particles. They're influenced by electric fields. If you have reverse bias junctions, you have electric fields in there. And those are how within pixels you collect either the photoelectrons or the photo holes, whether you're hole-based or electron-based sensor. And those are how you capture the electrons that end up being used to make image data. And so the number of those electrons determine how much, there's a measure of how much light came in, and so you can use an analog to digital converter and essentially create an image from that. So that's basically how those work. What I want to do is to talk about noise. And because these are sort of sample data systems, the primary noise that you cannot avoid is called photon shot noise. And it actually, if that's the only source of noise you have in one of these images, that is the lowest possible noise that you can have in one of the images. There's some other noise sources like dark signal, so that's the electrons that are accumulated within the pixels when no light is present. There's thermally generated charge that's in there, and that gets confused with the optically generated charge. Then there's some other forms of noise as well, including fixed patterns and other sorts of things that come in, read noise and so on. But the absolute floor on the noise, the best you can ever get, is just shot noise limited. So that's always our goal, is to be shot noise limited. And so it turns out that if you just look at the signal to noise ratio, it's the signal, those are the electrons that we've got divided by the noise. In this case, as I said, the best you can possibly do is shot noise. And so since the shot noise is actually numerically equal to the square root of the number of electrons that were in the signal, then when you do that ratio, it turns out that the signal to noise ratio, the best you can do is just the square root of the number of electrons that you've collected, because I've got the number of electrons divided by the square root of the number of electrons, so the math just works out to give you the square root of the number of electrons. So down in the lower corner here, I showed a log-log plot showing signal to noise ratio plotted against the number of electrons that are contained within the pixel. And you see a straight line, so that's what you'd expect with a square law relationship on log-log paper, and you would see a slope of 1/2, and that way you know you're really looking at shot noise. But you know, before we get a chance to go analyze what the sensor's going to do, we got to get light to the sensor. And so we're going to do that typically with some sort of focused optic. And the optic itself will seriously affect the light flux that makes it to the sensor. So in particular, you've got a focal length, and you've got a magnification, you've got transmission of the optics that are all involved. And so there's a little handy equation down here over in the lower right-hand side that shows how that works. But basically, the higher the magnification is in the lens, the more it's spreading the light out on the other side of the lens, so as you would expect, the flux of that light is reduced. And so if you have a high magnification lens, it tends to make the image not as bright. And if you've got a low magnification lens, it's all concentrated more in a more concentrated area, and so the optical flux is higher, so you get more signal quicker. So that's sort of the simplistic way of looking at it. But that's the first thing you got to do, is get your light through a lens and illuminate the surface of the sensor. And then once you've got it illuminating the surface of the sensor, you've got to time it. So you're going to have a shutter open time, and you're going to have a pixel of a certain size, and you're going to have an optical flux. So maybe it's so many lux, or you could convert it into units I like, which are photons per square centimeter per second. So that's different ways of representing the flux. But no matter what flux you have, over here on the vertical axis, we're showing the photometric exposure. So that's the dose. That's the amount of lux you've got times the exposure time. So it's lux seconds, which would basically wind up as units of photons per square centimeter when you do the necessary conversions. And then what you see is, I don't know why I've got this thing here. I'm also showing the pixel size on the horizontal axis. So the larger the pixel is, the more of that photon flux is going to be collected. So as you might imagine, large pixels for a given exposure time collect more signal more quickly. And so what we see are isophotons here. I'm showing 4,000 photons, 2,000 photons, and 1,000 photons. And you can see with the larger pixels, you need less light intensity. With the smaller pixels, you need more light intensity to get a given number of photons. Now, why do we care about the number of photons? Because that's ultimately going to establish our maximum signal-to-noise ratio we can possibly get. And over here, I've shown what those numbers are. So with 4,000 electrons, if I assume I'm just shot noise limited, my maximum theoretical signal-to-noise ratio would be, I got to put my glasses on, 63.25 decibels. And no matter what I do, I can't do better than that. So what this is saying is that you'd like to keep the shutter open a long time. If you're in dim light, you'd like to have big pixels. Okay, but you can't just go get arbitrarily big pixels, because if you've got a certain fixed number of them you need, you may wind up with a giant sensor that you can't afford to buy, number one, and number two, you can't afford to go put an optic in front of it because it's too big, too heavy, and too expensive. So there's a lot of interesting trade-offs to make there.